Thanks everybody for joining. Today's webinar is all about the future of high performance computing, and we're going to have a really great Q&A session with a big stacked lineup from the RAPIDS leadership team at NVIDIA. So the first thing I want you all to do, and this is kind of what I was dealing with just a second ago, is just get familiar with the interface a little bit in this Hop-In webinar. There's a chat window, should be on the right side there. If you go on to the stage tab, that is this current live event that you're in. So just go ahead and say hello in there. We want this to really be an interactive event for everybody to be able to ask questions and then even meet other attendees and everything. So go ahead and introduce yourself in that chat window while I'm talking here for a little bit, and then we're gonna keep going with the event. Cool. Okay, so in case you're wondering, my name is Aaron. I'm a senior data scientist at Saturn Cloud. And Saturn Cloud is a data science platform for data scientists to be able to do all of their work and do it quickly. My job is really to make sure that data scientists are working as efficiently as possible, using the best tools that they can in the Python ecosystem. And so what we're going through today is talking about high performance computing on GPUs with RAPIDS, and specifically we have with the RAPIDS team. So I'm going to start this by passing this over to Joshua Patterson, who's the Senior Director of AI Infrastructure at NVIDIA. He heads up the RAPIDS team, and I'm going to let him kind of introduce himself and then pass it over to everybody else for intros.
Sure. Just for sake of time, I think I'm going to introduce the team, and then during the Q&A, if they want to add more, I think that would be great. So I'm Josh Patterson. I'm the Senior Director of AI Infrastructure. I lead engineering for RAPIDS. So RAPIDS is our end-to-end data science libraries to really allow people to do all of their data science pipelines on the GPU. It's built typically in 2 layers, CUDA C++, and then some end-user API. The team primarily focuses on Python, which we're going to talk about today, but we also have other people who are adding other things to it at the end. We have a team working on Spark acceleration, so using Java as an end-user language. Blazing SQL is built fully on top of RAPIDS, which is more of a SQL interface. And we will continue to add more languages to support across the future. Quickly, there's John Z. He's one of our directors. He leads up QML, essentially a scikit learn drop-in replacement, which we'll talk more about. Keith Krause, he leads our data frame team. Essentially, the pandas, we scale that with Dask. And then finally, Brad Reese. He leads our cuGraph team. And both Keith and Brad are senior managers on the RAPIDS team. And Brad, essentially, we follow the NetworkX API, plus some other things that aren't in NetworkX. And we scale that also with Dask to multi-node, multi-GPU. So algorithms like PageRank and breadth first search, et cetera.
Great. Thanks, Josh. And Keith is here. He's going to be on in just a second. We're hitting a limit with the webinar software. We can only show 5 boxes at a time. So I'm going to show a couple slides just because I have the screen right now. I'm not going to spend a whole lot of time here, but just want to go over what Saturn Cloud is and what we do. Basically, what Saturn does is brings the best hardware on the cloud, pairing that with the best tools to scale data science in Python. So we're very much in the Python ecosystem. So we focus a lot on Dask for parallelism, and then we use RAPIDS for the kind of GPU accelerated computing. And so what we do is underneath and behind the scenes, we make sure that all of that tooling and technology is working, and we set up Docker and Kubernetes deployments. That way things are seamless to go from development into production. And a real quick teaser, and we're going to get into, again, more of what RAPIDS is and talk about a lot of these details, but this is an example of using Saturn Cloud's Dask cluster on the left to do a parallel distributed random forest model training really, really fast using a GPU. So in this case, if you see on the top right there, we're doing something with around 200 million records. And we did that with 20 nodes of a cluster that each had a GPU on them. And that only took 1 second to train a random forest with 100 trees, which in a normal environment, the data might be even too big to get it on a single node, and it would take minutes, several minutes, or even hours to do a similar training like this. So that's where RAPIDS comes in. And we talked about before how kind of a way that this session is going to work. It's just really going to be a Q&A time. And so we do want to know this. Josh, I'll let you kind of talk a little bit more about RAPIDS. One of the things that I was curious and had a question on was just the history of the project, like how it came to be, what inspired it, and if you can talk a little bit like that. I'll prep the slides and put the PDF inside so people can start looking at it.
Awesome. Yeah, so RAPIDS, it's kind of been a long journey. We joined in, well, I joined NVIDIA about 4 years, and several of the others on this call joined NVIDIA around that same time frame. John, automotive, our AV group, autonomous vehicles. Brad started off as an SA solution architect, and Keith started off as a solution engineer on the DGX team with myself. And what we realized is, there were some really great things we could do on the GPU, and the space was moving really fast. But going from one application to another, one framework to another even, was really painful. You were constantly moving data on and off the GPU, and copying and converting. And while that's kind of normal for CPU systems, it's a huge performance bottleneck to do all these mem copies. And so we started the GPU Open Analytics Initiative. We worked with a bunch in the community to really kind of set standards. We adopted Apache Arrow. Things were going really well, but we realized we needed to do more. We needed to move faster. We needed a full-fledged data frame library. We need to systematically build machine learning libraries. NVGraph was a great start, but we needed something a lot more holistic and end-user friendly. And so kind of an extension of GoAI, it kind of evolved into RAPIDS. And this is really end-to-end framework for doing all things data science. And our goal is to fill holes in the community where there aren't things. And so we don't have an array library, for instance. There's PyTorch, TensorFlow, CuPy, MXNet. There's a lot of ways you can do arrays. And so what we do is we bridge to these things with things like GLPack and the CUDA array interface. But we fill in the gaps where there aren't things. And so there wasn't a data frame library. So QDF is the data frame library. There are a few graph analytics packages, but QGraph kind of is the umbrella across all of them and tries to really unify the community. And there's always been like one algorithm here and there and a few different packages with GPU acceleration. But QML is meant to be this one-stop shop for all GPU accelerated algorithms, similar to scikit-learn. And so it's been an evolution, but our goal is to continue to build bridges, fewer walls, more bridges. We focus on interoperability and community.
So one other question I had, kind of a follow-on onto RAPIDS and everything, is RAPIDS is an open source project, right? You can see the GitHub, you can commit to it, you can open issues and everything. And a lot of people, you all work at NVIDIA, and a lot of people maybe tend to associate RAPIDS with NVIDIA. So I wanted to kind of ask you, of how does RAPIDS, what's NVIDIA's role in this kind of OSS ecosystem of RAPIDS? I guess is my question.
Yeah, great question. So RAPIDS, obviously, it pays our salaries. Thank you, NVIDIA. Sorry, NVIDIA pays our salaries. Thank you, NVIDIA. And we contribute to RAPIDS. It's in NVIDIA's best interest to have a really great open source ecosystem that allows data science to happen on the GPU seamlessly. NVIDIA incubates RAPIDS. It's kind of the main sponsor, but we do have contributors from many other places. Walmart, Capital One, Anaconda, Gunrock out of UC Davis, OmniSci, H2O. There's a lot. I wish I had the RAPIDS AI page pulled up in front of me. We have a lot of contributors, a lot of adopters. I think about a third of RAPIDS contributors now are outside of NVIDIA. And we would love for that to grow. So please contribute. Some of the great things that we're seeing is sometimes now it doesn't take a lot of developers to build a new library. QSignal, for instance, is strictly using Numba and CuPy. And it was really just someone's passion project that got so good that we're like, you know what, we should just maintain this as a library. And so, QSignal is a great example of how one person can really change an industry. We have a lot of people using QSignal today and saying really great things about it. It's a drop-in replacement for SciPy signal, and it's fast. So it's exactly what you want, something that's low cost to develop, low cost to maintain, and making people's lives a lot better. So, NVIDIA, we want to continue to grow the ecosystem, and we want more people to adopt it and more libraries to be accelerated.
Awesome. And kind of on the tone of acceleration and speeding things up, there's a lot of, I see a lot of the stuff that comes out from Rapids and the team of like really exciting benchmarks where things are like way faster than quote unquote traditional ways of doing it. And one of those that I noticed was this TPC-BB benchmark. That's something that seems like a standard like big data benchmark that Rapids kind of blew out of the water. And so the question is, what is that first? And then how does that relate to actually, doing things day to day, like in an enterprise setting?
Yeah. We have a great blog about it. I'm going to drop it into the chat window after I get done talking. But essentially, it's 30 queries. It's a benchmark that normally takes hours. We did it in about 15 minutes on our latest DGX A100 systems. Those are 8 GPUs connected by NVLink, NVSwitch actually, which is our next gen beyond NVLink. And the A100s are our latest GPU. And essentially, we're getting about 20x the speed up server for server using 16 servers versus 16 CPU servers. And that equates to about a 7x TCO improvement. So when you do like cost of the hardware times the time it takes to run the benchmark, we're 7 times better. And I think that's really important. Not only are we doing things faster, they're cheaper as well. And so it's unstructured, semi-structured, and structured types of queries, everything from NLP and like name entity recognition to kind of like forecasting in these workflows. And they represent basically what people do in finance, retail, telcos, and many other industries. So it's just a standard benchmark of reading from disk, doing pre-processing, feeding that into machine learning, and then having some type of meaningful result.
Great, and that's really exciting to see. Kind of the cost of ownership reductions is pretty awesome, because people tend to sometimes associate GPUs with premiums and being more expensive and luxury, but now because of the performance gains that you get, it's actually cheaper and more cost effective to use the GPUs. So that's cool. One other thing that I have, and then we'll start jumping into maybe some other audience questions, is this is recent. I think the last week or two, I saw some stuff about streaming and coup streams. Seems like that was just released. Curious, like, what is that? Do we see the same kind of level of performance improvements like that other benchmark? And what's the future of streaming on GPUs?
So streaming on GPUs is not new. We've had TensorRT at NVIDIA for years, literally. TensorRT is even older than Rapid. So inferencing and streaming inferencing on GPUs is a thing that's been very useful. We've just brought it to tabular data. So Keith can talk about coup streams a little bit more, but also I want to talk about Phil, our forest inferencing library that we released, like 6 releases ago now, 0.9, John?
Yeah, 0.9 is right.
Yeah, so John, quickly, let's talk about Phil, and then Keith, tell us about what's going on with coup streams.
Sure, absolutely. A lot of customers, a huge number of our customers are using tree-based models, whether they're random forest, XGBoost, like GBM, kind of all over the map. And the training can be compute intensive. So we've done a lot to speed that up in XGBoost and RF. But we were increasingly seeing customers want to do things like rescore all of my data every night for all of my customers using this huge tree model I've built with 1,000 trees. And it's one of those things, you start small and then people keep adding more and more and more cloud instances to their nightly batch job through this scoring. And we realized that was something we could really speed up on GPU. So Forest Inference Library is really slim. It's easy to deploy. It's like 2 lines of Python code to do inference. And it just reads whatever your existing model is, whether it's and brings that onto GPU. Even if you trained the model 2 years ago on CPU, you can often typically load it in a fill and inference it there. So really amazing batch throughput, like 35x faster than what you're getting on CPU typically. So you can really reduce the need to spend a lot of time doing batch scoring. So definitely cool and neat to kind of jump into the inference world there too for structured data. Thanks for posting the blog there, Mike. Mike just put a link to the blog about Phil in the chat window there.
Cool. And then as far as QStreams goes, so QStreams has a few different pieces to it. So kind of as Josh mentioned, the idea behind QStreams is to GPU accelerate stream processing in Python. But in order to do that, we need to do a few different things. So one, we took the streams Python library, which is a Python stream processing library that was built on top of Pandas data frames and Dask. We basically took that library as a starting point, and similar to the work that we've done in QDF to accelerate data frame operations using GPUs, we similarly did the work in QDF to make it compatible with streams so that it can just natively target QDF as if it was targeting Pandas and get GPU accelerated processing that way. So that was our first step. We did that, and what we quickly realized is that there were a lot of key bottlenecks surrounding the processing, mainly on input and output. And basically, what we saw is that a lot of people use Kafka as a pub sub system. Oh, I think people are saying that it has dropped.
Okay. All right. Here's what I'm thinking, and hopefully everybody can see the chat. We are having a lot of technical difficulties with Hopin. I'm gonna say let's go to Zoom. I'm gonna start up a Zoom and then move over to. All right. Sorry about that again, everybody. I think we're up and running now on Zoom, so we should be good to go. I think we left it off with Keith. We were talking a little bit about QStreams and then Forest Inference Library. And so the next thing is it's kind of open now. Like I do have some more questions that I can ask the team. But again, if you have anything specifically as an attendee that you want to hear about from the RAPIDS team, feel free to drop it in the chat, and I'll kind of curate them. One question that I have, and we talked a little bit about like parallelism, but from immediately it might not be kind of clear what that means. So my question is that when we think about like non-GPU computing, right? There's the CPU and then using main memory. Some of us have laptops that have like 30 gigs of RAM. We can get EC2 instances that have 60, hundreds of gigs of RAM. And so when you think about GPUs, they tend to have kind of a little bit more limitations for like a single GPU. A typical one might have like 16 gigs of RAM or maybe a little bit more. What happens when my data kind of exceeds the memory of a single GPU? And I'll kind of open that up to everybody.
So, there's two parts to your question. First, you were talking about parallelism and the amount of memory. So for parallelism, on your CPUs, you're limited by the number of cores. And a typical CPU, you can have, 8, 12, 16 cores. Hyper-threading, you can double that. A GPU, you can have 5,000 cores. So you have more parallelism. The issue then, as you were mentioning, is the amount of available memory. And there's two ways that we can approach that. One is hopefully you can break your problem up into smaller sections. Two, we have something called unified memory where the GPU will dynamically page things in and out of memory as needed. There is a slight overhead for doing that. Or what we try to do is have people go to multi-GPU solutions. So we, under the covers, use nickel, MPI, and all, so that we do message passing among a whole collection of GPUs. So now we can scale to larger and larger amounts of what we call, device memory.
Yeah, that's absolutely right. And I think that's one of the things that people are like, oh, well, GPUs are expensive, so I only want to use a few of them. But then they're like, I'm not getting the right performance because my data set is massive. And we have to, remind people sometimes, no, it's okay to scale out. It'll just, it'll only take a few seconds or a few minutes, and then you can, scale those GPUs back down or give them to the next person in the queue who needs to use them.
Hey, what's up? You can come into here.
And so, one of the things that I think is somewhat forgotten is that with Rapids, we can really do like a lot of the data science workflow on the GPU. And because of that, in fact, not a lot of it, with GPU-XPB, we show that we can do the full thing on the GPU. not leaving the GPU memory, even for things that aren't as efficient on the GPU, not having to pay that mem copy penalty really allows these full pipelines to have really great acceleration and cost benefit.
That's great. Yeah, and I mean, that's kind of partially the example that I showed before was doing something on 20 different machines that each had a GPU. And so that's great. So, okay. Cool. Another one that I asked is that, you know, when you think about like working in this new library, people might have a lot of workflows already built into like pandas or other kind of just like Python stuff. What if somebody wanted to do something inside of Rapids that maybe isn't necessarily like directly supported through like a first level interface? Like, are there capacities for you to define functions or anything like that?
Yeah, that's a great question. Keith, do you want to jump in?
Yeah, so what I would say in general, where we're striving for with the QDF API, for example, in relation to pandas, is any differences from the pandas API are basically being treated as a bug unless there is an explicit decision not to support it. And kind of the only examples that I can give is, for example, we won't allow you to write like for loops over QDF objects. And the reason behind that is just doing Python iteration over those things would be horribly painfully slow, like much slower than doing it on the CPU. And we will error in a very informative way to explicitly instruct you that, hey, if you need to iterate, go to a host object like pandas or arrow to do so. For things like user-defined functions, we actually have a lot of support where we will take that user-defined function that you give us and pipeline it through another open source project called Numba, which is a just-in-time Python compiler. And it will basically take that Python function you give it and lower it down into a vectorized GPU kernel and execute that on the GPU. And so what we see is user-defined functions are actually one of the areas that we will get massive, massive speed-ups over doing it in pandas, because pandas will just do it via normal Python iteration, which goes very slow.
Got it. That's great. So, I mean, you can really move over a lot of workflows that way. So that's awesome. Another question is I've seen this library called NVTabular, and that looks pretty interesting about like doing like recommender systems and processing. It seems like does it interact with Rapids? Is that a separate library? What is that, and what does that do?
Keith, do you want to jump onto this one again?
Sure. So NVTabular is an NVIDIA library that's built basically entirely on top of QDF, along with some other GPU functionality. And so basically it's built really in kind of like the recommender systems area, but it's built to do kind of all of your feature engineering, pre-processing, data loading that you would normally do in these typical kind of like tabular data recommendation system type problems, and then allow for really nice, easy interoperability with deep learning frameworks like TensorFlow and PyTorch and whatnot. So it leverages everything that we've built in QDF within Rapids for all of its kind of fast tabular data handling, but then adds some additional recommendation system specific functionality on top of it.
One other thing I want to add is NVTabular is a part of Merlin, and so Merlin is kind of an NVIDIA package for recommenders in general. So NVTabular is the data processing side, as Keith said, Dask QDF under the hood, but they spend a lot of time simplifying it and building it very specifically for recommender use cases. And then there's a huge CTR side, which is actually a framework for training recommendations. It's similar to PyTorch and TensorFlow, and you can also use PyTorch and TensorFlow instead of huge CTR. But it's just another way of showing how Rapids is playing with an ecosystem versus trying to just take over something. And it goes back to what I was talking about earlier with DL pack and CUDA array interface. Because we have interoperability, people can build these data loaders where they use Dask QDF to do the manipulation and then load that directly into a deep learning framework. And so, we love to see more use cases like that.
Yeah, that's great. And actually, kind of, I do want to take a little bit of a step back and think about for data science, maybe data scientists that are maybe used to using GPUs for deep learning tasks. They might be already familiar with what CUDA is and what it does. But for people maybe who are coming into this a little bit newer, not used to using GPUs, and you hear the terms about NVIDIA GPUs, you hear CUDA and things like that. Just first of all, what is it? And then as a data scientist who wants to use Rapids and take advantage of the GPU acceleration, how much do I need to know about CUDA itself and interacting with it?
Hopefully none. Our goal is for things to be done fully in Python. All of TPC-XBB was pure Python. Blazing SQL, pure SQL, NVTabular, it's just Python. The goal is we spend a lot of time doing all the hard work of going from CUDA to CUDA C++ to our primitive libraries, and then using other libraries like Thrust and Cub and Jitify and Nickel and all these different things to build out this infrastructure. And then we use Python to bind that to Python. So the end user really doesn't have to think about what's under the hood. They just write code, just typical normal things that you would do with DAS, and it just scales to GPUs and works really well. And we've all taken this kind of philosophy across all of our libraries. And so we have really, in Rapids, two end users, library devs and library devs. So at the CUDA C++ layer, it's for people who want to integrate Rapids directly into their software. And then also at like the Python or Java layer, it's for other people to embed into other things. And so we work closely with the DAS community, you all at Saturn Cloud, and others to really allow your user to have this really great experience. But it is really taking these modular building blocks and just exposing them in the right way so it just seamlessly works with other frameworks.
Yeah, and just to add on to what Josh said, we strive that you never need to go down to the CUDA layer. That being said, if you are a power user and you have some of your own CUDA code that you want to kind of integrate with Rapids, we do not hide that from you in any way. Where if you want to just get down to your raw data pointers and be able to pass those into things that you want to, we give you a nice clean path in order to get to those pointers so you can do something completely custom, do whatever you want to do in that way.
Yeah, and if you look at the Python code, you won't really see references to GPUs at all. You won't even be able to tell that you're on a GPU. It'll just feel like you're normally writing pandas or scikit-learn or something.
That's great. That's awesome. So something actually that I think is related a little bit to what we were talking about with NVTabular. We had somebody in the audience ask a question around like feature stores or feature engineering. What does that workflow kind of look like when you're using GPUs and the Rapids ecosystem?
Yeah, so there are a lot of ways to do feature engineering from Rapids. So you can either use Dask, which I think most are most familiar with. And so basically Dask data frame, we follow the Pandas API, so we can just kind of plug seamlessly into the Dask data frame. We also do work with like UCX to accelerate Dask data movement. So there's more speed ups as well. Then there's Blazing SQL. So if you just want to write things in SQL, read this Parquet table and do some manipulation and then write it back out to Parquet. That's transparently done through SQL. NVTabular, if you want to do something specialized for recommenders. QStreams is really just streams plus Dask plus QDF and a nice meta package with a few, really slick, integrations with Kafka to interact with its C++ layer under the hood. So the user just writes their pandas code in a streaming workflow, and it just pulls that data from Kafka really quickly, pushes it into a GPU, does something, and just keeps going, whether it's stateful or stateless. And so our goal is to support feature engineering in a lot of ways. And what we're now starting to see is these like abstractions on abstractions. You have things like the Plotly integration, where it's using Dask and other backends, and then allowing people to basically have an interactive BI tool, all built in Python, but the end user can just kind of experience it through their browser. And so So yeah, there's a lot of ways to do this today. There are a lot of things that are powered by Rapids.
Yeah, and just to add to that, specifically as far as like feature engineering tools, there have been tools built on top of Pandas and on top of Dask. And because we basically follow the Pandas API and we can just plug in naturally under Dask, you can just naturally use Rapids libraries in those tools. And so like notably, there's a platform called Bumblebee, which is a data cleaning platform, and another one called Feature Tools that because they just nicely talk to Pandas and talk to Dask, they can just naturally talk to Rapids and take full advantage of GPU acceleration that we're giving you.
I would just add one more thing to pile on, which is that to the extent that sort of like Keith and Josh talking about following the Pandas API, a lot of people already have an existing solution for building on top of, say, scikit-learn's pipelines or scikit-learn pre-processing tools for feature engineering. QML really matches those APIs as well. We have a lot of core vectorizing and featurization tools like one-hot encoding, or if you're doing text and you want to do TF-IDF vectorization, which is super popular, those are out now. Even more extensive suite of scikit-learn compatible pre-processing on GPU is coming in the next release and is actually in a pull request right now. And one of the things we always encourage people is that you can just pull down nightlies, you can pull down directly from GitHub. It's really easy to get started with that if you ever want a preview of what's coming up. So if you're really interested in scikit-learn pre-processing, grab an 0.16 nightly in the next week or so, and you'll be able to play around with that too and help shape the future of that too.
Great, and I think you jumped right into the next question. That's exactly what somebody actually asking about that compatibility. So that's great. About just like scikit-learn working with QML. Is there stuff like if there's not yet a QML model or classifier or estimator or something, is it still possible to use that?
Yeah, absolutely. One of the nice things about scikit-learn API, which we've matched closely, is that it's very composable, right? You can have different building blocks in your pipeline that all stream together smoothly. To get the greatest performance, you're going to want to keep everything on GPU. And so if you want to keep everything on GPU, then yeah, you're going to need the libraries all to be in GPU. We do support this sort of whatever you put in is what you get out as the default for QML. So if you want to work and say, I'm going to pass NumPy data into my model, QML will pull it onto the GPU for you, send it back out onto CPU as well, and then you can pass that into another CPU element of the pipeline. That said, you are going to pay the price of going back and forth over the bus to the host CPU as well. So we do try and keep things on GPU as much as possible. Yeah, you can mix and match for something that's not supported yet.
Awesome. That makes sense. That makes a lot of sense. One other one is, and I think this can kind of be like a roundtable question because I think everybody might have a little bit different answers about this because it seems like there's a lot happening. But what are you most excited about in the next Rapids release? I think the next one is it 0.16 or 15? It's moving kind of quickly, so.
Yeah, so 0.16.
0.16, yeah.
I'm going to give kind of the most PC answer. I'm most excited about our Ampere support in this release. Finally, CUDA 11's out and GA'd, and hopefully in the very near future, we'll have a release, and it'll have Ampere support. So those really big 16 A100 instances on GCP, the first cloud to adopt A100s, we'll be able to run Rapids. So you can just fire up a 16 GPU Dask cluster all on a single server connected by NV switch, and do some pretty awesome things. After that, I'm particularly excited about some of the graph stuff, but I'm going to let Brad talk about that.
So yeah, in graph, we are now really going after the really big graphs. So we were able to scale out to, 8 GPUs or 16 GPUs, and now we're really redoing the code so that we can hit, 128 or more GPUs, so we can tackle these large, Facebook-sized graphs, all at, blazing rapid speed. I'm also very excited really more about the interoperability between all the products and how they're becoming more seamless. So you just think in terms of rapids and not, graph or ML.
Yeah, Keith and John, do you have any differing opinions?
Yeah, not differing so much, but from ML, I think one of the things we're most interested in kind of goes back to that earlier question. As we've gotten to a greater level of completeness with scikit-learn APIs, we're seeing more and more people plugging QML into various kinds of meta estimators. So that could be like, I want to do stacking and train 20 models and stack all the results together. I want to build custom boosting, or I want to do hyperparameter optimization. And those are things that typically require someone to fit 10, 20, or 1,000 models, depending on how extensive you want to get. So we're seeing that support grow really significantly and having a lot of investment in hyperopt type products, which I think is super exciting. And you just see these ridiculous speedups. And going along with that, for O16, rolling out the new pre-processing support, I think will really help. That is expanded scikit-learn compatible pre-processing support will help people move more and more of these full pipelines into those libraries, so you're doing proper hyperparameter optimization over your input pipelines, your feature engineering, as well as the model itself, which really can give you more accurate hyperparameter optimization and a lot of speed too. So I'm really excited about that all coming together in the shape of hyperopt.
Yeah, from the QDF side, I just want to give one point of clarification. Josh mentioned the next release is 0.16, and that's because the team is actually executing the 0.15 release as we speak right now. So hopefully we should have packages up either later today or tomorrow for 0.15 in our normal Conda channels. But for 0.15, QDF had a massive release where we added a lot of really cool things. One of the most excited, from my side, one of the most exciting things was we added a lot more D-type support, where we added unsigned integers, we added time deltas, and we added the beginnings of a new native list type, where you will be able to have nested data in your QDF columns, which is really exciting and people have been asking for a long time. In addition to that, we mentioned earlier with streams, that we added a native C++ accelerated Kafka reader that basically you can specify a Kafka as a data source and then feed it into any of our readers of like CSV or JSON or Avro and basically get huge speed ups versus using like normal Python Kafka libraries that way. And then I would add the last thing that I'm really excited about is we started to add a lot of NLP pre-processing functionality into QDF, where we added a BERT subword tokenizer into QDF, and it basically blows the performance of the kind of current state of the art out of the water, where I believe that is Hugging Face recently did a Rust implementation of it that got like a 10x or 100x speed up over the normal Python one. And I think we got another 10x to 100x over that Rust implementation as well. And so for people that are using kind of BERT or other NLP type workloads, we're starting to build up a bunch of pre-processing functionality for those workloads. And it's really exciting to see that support grow and see those use cases grow.
Yeah, the NLP stuff is awesome. It's very popular.
And thank you, Keith. I clearly am not sleeping enough these days. We're releasing 0.15 today, and 16 will come out in October. One other thing I would like to add, as every release, it just comes up further and further of a web of different things of what we're connected to. With this release, I think we will officially have uniform coverage of integration with deep learning frameworks. So TensorFlow 2.3, which is coming out soon, will support DLPack, PyTorch, DLPack, Numba CUDA array interface. And so now this is kind of the first release where every DL framework, we can also have interop with them. And so it's less of something that we did, but more so of the community is adopting these standards that we've really been championing because they have a reason to. Because now they get this great data frame library and all these QML models and graph analytics algorithms. So by giving back to the community, we've also moved a lot forward in interoperability. So yeah, so that's exciting, and we have some really great things, just in the works in 16 and 17, and the team just kind of, busy doing work for the rest of the year. One other external thing that I'm excited about is Blazing SQL. They're getting really close to finalizing their UCX integration. And so that should be coming out in their next release, probably not 0.15, but in 16. But their out of core is really been baked and hardened in this release. And so they're doing some really large scale ETL and SQL with a very small GPU footprint. And so we're really excited about working with the Blazing SQL team and all that they've contributed to the Rapids ecosystem.
Awesome. That's a lot of stuff happening, a lot of stuff coming out. Very exciting. I have one, and we're starting to run out of time. I have one other one, which is, I guess, a little bit more philosophical on end. And it's about, I hear a lot, and the CEO of NVIDIA, Jensen Huang, has said this kind of in a number of occasions about something to the effect of like Moore's law isn't possible, isn't happening anymore the same way that we've seen with CPUs. So what does that mean, like, in terms of computing hardware in GPUs, but in general, what does that mean about the future of high performance computing?
So data is going to keep growing, and that's just inevitable. And CPU performance doesn't continue to grow. It's somewhat finite. Sorry. And so one of the things is we're moving to a place where coprocessors are just kind of necessary. And I think the thing with this kind of end of Moore's law is it won't really be this coprocessor processor. Workloads are going to be more GPU centric, where the GPU is the main kind of workhorse. And I think Rapids is showing that it's much cheaper if you don't treat the GPU like as an offload for computationally intensive things, just push everything there. And I think that's going to become more of the standard as people's data sizes continue to grow, as their algorithms continue to become more complex with some of these BERT and BERT derivative type frameworks. And so yeah, GPUs are going to be very common in the data center in the future, and that's just really exciting.
Awesome. Okay, does anybody on the Rapids team have anything burning that they wanted to talk about? Because that's kind of it as far as questions. I know we're almost out of time. I have one final one, but in case anybody wanted to say something.
I mean, one of the things we haven't talked about really is how you can not only get your algorithms to run faster, but how you can do more with your algorithms. So we talked about feature engineering, and most times people just pull out the key features and they use that for training. But now they have the power to actually say, instead of just using the top 3 features, I am going to use all my features and still have answers in reasonable time. Still faster than what it was on a CPU. Against 3, you can do 20 or more. So we encourage people to really start exploring their data more than they were.
Yeah, I would add to what Brad said. It's a really common pattern that we see from Rapids users, where their first step is they take what they have, they use Rapids, and they get a huge speed up and enjoy that speed up. Then the second step is they realize that, oh, instead of like, I was doing something in 24 hours, I can now do that in minutes. I still have the other 23 hours and however many minutes to work with before I'm required to give this answer. I can do a whole lot more feature engineering, a whole lot more modeling, and basically improve my whole process and get better answers in order to do that. Where with Rapids, like we like to tout big speed ups and everything, but most of the time the speed ups are great, but really we fundamentally just change the approach to problems because you can do so much more in the same time period. And it allows you to basically change your business decisions based on it.
Yeah, and that's a good point, and something that we talk a lot about with Saturn and with doing GPU processing and stuff, because people again had this idea in their mind that GPUs are more expensive, but in reality they're not. You can rent them on the cloud. You can and your processing is so much faster. And what we talk about a lot is that the cost of a data scientist full-time working on something or waiting for something is much more expensive than the hardware that you're going to pay for by using GPUs. So if somebody's just sitting around, or they have to run something overnight, or they have to run something over several hours, that's just lost productivity, and that becomes really expensive as far as people's time. So that's a really good point.
Well, and one other thing to add to that, it's really expensive not to have higher accuracy or whatever your measure of performance is. And so if you can iterate a model, just a few more times and get 1 or 2% more accuracy, and you're a large retailer or a bank, that's a substantial change to your business. And so it's one of those things where when we talk about TCO, it's strictly just the hardware and time. I think what you said about the data scientists and enabling them to do more because they're in a very expensive resource. And then also just kind of the bottom line, this is the best model I can get out in a week. Whereas I can find a much better model using hyperparameter optimization in like a few hours. Now we can iterate these models, push them into production a lot faster, always have best models, in inference. And these things really start to add up to businesses quickly.
Yeah, absolutely. So we just have a couple more minutes. I have one already like pre-planned question, and that's kind of just, this sounds awesome, right? All of these speed ups, all these new things happening. How do I actually get started? And because it's an open source project, how do I contribute? How do I join in?
Yeah, I love ending on this. So first off, our GitHub is extremely active. If you're not a GitHub person and you just want to learn more about the community, go to rapids.ai. We have a Slack channel. You can ask questions on Stack Overflow. But yeah, getting started. Conda install, just like Pandas or scikit-learn. You can pull our container from Docker Hub or NGC, and also Saturn Cloud. Thanks you guys for making it really easy for people to use Rapids. And I don't mean that jokingly. It really is great that you all are making it so easy for people to use Rapids. It's kind of becoming very common now. I think most clouds have a way to at least get a GPU and Rapids running very quickly. We have integration with all the major clouds, all the major machine learning frameworks in the cloud. Yeah, we're kind of becoming everywhere. But I think when you really want to become a power user and start using multiple GPUs, thank you, Saturn Cloud, for making that really easy to scale up a DAS cluster. And just kind of unleash, dozens of GPUs on a problem.
Yeah, and thanks for that segue. That's a perfect ending into our kind of last slide here. And if you do want to get going, it is pretty quick and easy to get going on Saturn. It installs inside your AWS account. You can get a free trial and then kind of just choose a GPU instance and then launch a cluster, and you can run some of the examples that I had shown before, like on that distributed random forest and some other stuff. But we're out of time. I want to thank you again so much, Josh and Keith and Brad and John. Thank you for joining. And this was a really informative session. And thank you all the attendees and everybody for being patient with us through our technical difficulties. It looks like everybody was able to come over to the Zoom, and we'll work on stitching together a recording of this so that way we can refer to that again.
Thanks, everyone.
Thanks.
Thanks for having us.
Bye, everybody.